All right. Well, hello and good morning, and welcome to our class, Stats 101C, Statistical Models and Data Mining. And if I don't know, for some of you, it's welcome back to school. I hope your summer's been going okay, and some of you never left school because you were here during session A, and if that's the case, hang in there. Another 6 weeks to go. Just thought we'll get started. We'll, I guess, briefly go through the syllabus. The syllabus, it gets longer every. It feels like it gets longer every year, and now I'm up to 9 pages with a table of contents, which it's like too much now. But anyway, this class. What is this class? This class covers. What does it say? Introduces practical tools for modeling complex data and making predictions. And so basically, it's the focus of this class is going to be kind of applied methods for machine learning, data modeling, data mining, things of that nature. I'm going to teach things using R and the tidyverse. I know that's a bit controversial just because Python is also very popular, and there's scikit-learn, and I would say tidy models and scikit-learn, they both kind of cover similar territory. I am a big fan of tidy models and the way it structures kind of the process. Certainly you can do similar things. It's, in my opinion, it's not as elegant in Python and scikit-learn, but I also think the skills, they translate over very, very easily. Like if you get tidy models down pretty well, like you can pick up scikit-learn fairly easily and whatnot. And but anyway, that's what we're kind of looking at. This is very practical. You'll have like these final projects and whatnot, and that's going to be kind of like half your course grade. But anyway, okay, let's take a look. All right, so here we are. We meet here, 8 a.m. I hope to see you guys. I like seeing faces. I know 8 a.m. is rough, okay, and I record my videos. Some of my colleagues were like, don't record your videos if you have an 8 a.m. because then nobody's going to come. They'll just watch the videos later. And, I'm going to risk it because I'm going to record it because I think it's useful. Especially, I know some of you will miss. That's okay. Of course, I prefer you being here. But if the videos are useful, then that's that. But for me, I always find it hard to stay focused during a 2-hour video, right? Especially if it's like an educational video, it's so easy to start doing something else. And so for me, just sitting in the classroom where it's distractions are limited, I find it better. So, but do what you need to do. Okay. All right. Office hours. So it's a little embarrassing to say, but I've come to terms and I've come to peace about this fact about myself. But I'm really bad at email. I'm really bad at written forms of communication. I'm the person that you text and I just leave you on read for forever, and it's not that I'm trying to be rude. It's just for whatever reason my brain has a hard time with responding. Now that with phones there's kind of one text replies, right? Like it auto predicts what you might say back, or you can just tap hold and give a thumbs up emoji in response. like that has like revolutionized communication with my wife, because I used to just not say anything. It's like the worst. And now at least I can say thumbs up and I got your message. But it's still like, I'm so terrible. And like email, you can email me and sometimes I respond. Sometimes it takes me forever to respond. Some of you might have already experienced that. Like you've sent me emails and it just takes me like forever to respond. And I'm not trying to be rude. It's just, I don't know. It's hard for me. I don't know. Okay. But so to kind of make up for it, I have office hours like multiple times during the week. I'll be signed in on Zoom. You come there. I will, you have an issue, something, we'll try to get it resolved during office hours. Okay. And then I use email for like kind of like paper receipts. So if we talk about something in office hours and we say, all right, I gave you an extension for the homework or whatever, then I'll send you a little email in office hours that is just like, this is just to confirm what we discussed, that you get an extension for this or something like that. Okay. So come to office hours, use Zoom. That'll be the better form of communication. If these times don't work, just, you can send me emails, but just please be patient. I'm patient with me. Okay. As far as this class goes, I only have 3 homework assignments planned, and they should be not too hard. Just kind of like practice for solidifying like what we've covered in class, and for you to kind of get practice and things. And these are my planned due dates. I got to finish getting the Gradescope website set up for you to submit your homeworks. I'll also send you invitations to a learning platform called DataCamp, and I'll assign some kind of courses and interactive chapters there. Okay. Here's the list of topics that we'll cover, and et cetera, et cetera. Okay. What else do I need to say? All right. Our 2 textbooks you can download or read in your browser for free. I mean, you can also find these textbooks like on Amazon and purchase them, but I think, I don't know, we probably do 90% of our reading on the screen anyway, right? Maybe 99% of our reading on the screen. And so you can just read these books for free in your browser, okay? And let's see, I'll have lecture quizzes, which just kind of quizzes related to the lecture that you have to respond to. Okay, and then we'll have these final projects. And I'll talk about the final projects in maybe next week or so. But basically, we'll have kind of two projects. One's going to be a classification project. One's going to be a regression project. And these will be... I don't know if you're familiar with Kaggle. There's Kaggle competition leaderboards, and it will be, the way it's going to be set up is there's going to be, a big data set, and it will be split into like basically training data and testing data. The testing is like kept, hidden and secret. Okay. And then, I guess the responses to the test. So this is all going to be supervised learning. You fit your models and whatever, you make predictions, and then you get evaluated on the accuracy of your predictions. And it will be kind of ranked, and you'll get, so that will be the final project. There's there's a bit of randomness at play, just because in the test data set, there's like the public leaderboard and the private leaderboard, and the final rankings are evaluated on the private leaderboard. So anyway, right now I'm in the process of kind of just finalizing the data sets that we'll use for the projects, and I'll talk about those things. Okay, I don't know if there's anything else I need to talk about regarding the homework. I got a whole bunch of stuff written here regarding homeworks and whatnot. It's like all of this fine print that the things get longer and longer each quarter because Always something comes up. And then just kind of general policies here. Okay. I don't know. Any general questions about the class? Yeah.
For your office hours, I know you talked about Zoom or anything.
So I'm on campus basically. So I teach this class at 8 a.m. and then I have another class that starts at 11. So I have like an hour in between this class and the next class. So after class, you can always come up to me and we can talk. So basically Tuesdays and Thursdays after class. And then for my next class, I'll be like Tuesdays and Thursdays before class will be my in-person office hours. Yeah, I guess I should add that to the website. Okay. All right. Let me tell you. I should introduce myself. I don't know if I ever said. Okay, so I'm Miles Chen. That's me. I give you permission to call me by my first name, Miles. That's fine. If that feels weird to you, you can, Professor Chen, Dr. Chen. That's also fine. No, no problem with that. And yeah, I'm so grateful to have this job to teach statistics, data science. It truly does feel like a dream come true. Working for UCLA, and I don't know. It's like you guys are good students. I talk to other people who are professors at other institutions, and so many people are complaining about kids these days and stuff like that. But I don't know. I don't feel that way. Okay, I don't feel that way. I feel like I'm so lucky. I feel like I don't know. I haven't met you guys, or like maybe I've met you guys and I've forgotten. But I just feel like UCLA students are really great, and so I appreciate that. I'll tell you a little bit about myself. I have a wife and two girls. So this is us right here. This was at a friend's wedding. So my girls. This is not a good picture.
No.
My daughter's here, by the way. This is my younger one because school for her starts next week, so she has to tag along with me. But anyway, this was at a friend's wedding, and then I've got a dog. This is the best dog in the world. His name is Firu. I don't know. Anyway, everybody's dog is the best, but truly mine really is. And then against my better judgment, I allowed my kids wanted a rabbit, so here we go. This is Bun Bun. Our bunny rabbit. Okay. And okay, anyway, that's a little bit about me. And all right, let's talk about I can't even spell statistical models here. Okay, let's get into this. What did I write? Welcome to summer session. Okay. All right, so a few other things. All right. This is going to be focused on application, lots of machine learning. And 6 weeks goes fast. Like you thought quarter system was fast. The summer session 6 weeks is even faster. And it's tough. Okay. Our textbooks. Oh yes. We're going to be using tidy models, and the documentation's all available in the browser. So this is going to be also an important thing, like an important skill, is the ability to read documentation. So you're going to, at some point when you're working, you're going to be using a package that you've never used before, using some functions, using some applications that you've never used before. And you're going to have to figure out how to use it yourself. And the best resources will be, like the official will be the documentation, and you have to be able to read documentation. Other people will produce tutorials and stuff, but read the documentation for the class. Okay, what did I write? My vision for the class says we'll work through a few chapters of this textbook, Introduction to Statistical Learning. This statistical learning is kind of like another way of saying machine learning, but I guess it's like machine learning with maybe more foundations in statistics, but it's the same kind of idea. The idea of statistical learning, machine learning, they're kind of pretty much the same thing. Okay, and it's I think regarded by many to be one of the best introductory texts. Okay, the people who wrote it are up at Stanford, and they started off. They wrote it in R, and then they now have. If I click this, Stat Learning, they now have a version of it. It says an introduction to statistical learning with applications in R, and then they also have an introduction to statistical learning with applications in Python. This book is like exactly the same. It's just they basically each chapter they changed the lab part into Python, and they just kind of translated it over. But like it's like the same diagrams and the stuff that were all kind of created in R originally. But anyway, I shouldn't have clicked that link. It's a good book. Okay. And yeah, unfortunately, there's a lot I want to cover, but we're not going to have time for everything. I'm going to focus a lot on kind of like practical stuff. And there's always, as far as teaching and pedagogy goes, there's a debate like how much practical and how much theoretical. This class is going to focus more on the practical side, for better or worse. Okay. I'll assign homework, and so I want to talk about this. The homework I assign is intended to be a decent amount of it's always a challenge to find the right mix of challenge and difficulty, right? Sometimes it's too easy, sometimes it's too hard. Trying to get it right is always a little bit tough, okay? Here's the truth right now, okay? We are, at the point where you can find all of the answers that you want, either just by searching for the answers directly, or you can copy and paste your question into, the AI, ChatGPT, or, Gemini or whatever, and it's going to spit out an answer, okay? And I strongly encourage you not to do that, okay? And of course, everybody says this, but I'm a true believer in, I believe in learning. That's why I'm here at the university teaching, and I think you are also here taking this class because you want to learn, right? We understand this when it comes to, I don't know if you ever go to the gym to work out. There's like this very intrinsic understanding of how this works at the gym, in that like if the point of going to the gym and lifting weights is for you to get stronger, and it's not so that the weights get lifted up off the ground, okay? And if you want to get stronger, you have to kind of push yourself at the gym. You can't just pick up 1 pound weights and say, all right, this is my exercise, right? I lifted 1 pound weights. I did, 20 reps of 1 pound weights. You can't expect that to help you get stronger, right? You kind of have to find the right limit of like, this is what I'm capable of doing now, and I want to try to push myself a little bit further, right? And it's hard. And then when you're done, you rest, and then you come back and you get stronger, right? That's how it works at the gym. And the learning works the same way, okay? If you only do things that are like easy and comfortable, you're like, oh, okay, I can do, this level math, I can do this level coding, it's real easy for me. That's like lifting the 1 pound weights, okay? And then to really kind of grow and learn, you have to kind of find the right mix of challenge, okay? And if you find certain things are too easy, make it a little bit tougher on yourself by, just say, all right, I'm going to try to do this without looking up too much stuff on Google, right? I'm going to try to force myself to remember some of these things. And it's hard. Our tendency is not to want to do these things. But the classroom, this class offers, basically a very low stakes, safe environment where you have the freedom to, make a mistake. And the worst thing that's going to happen is you lose a few points, okay? It's not like you're going to bring down the production system at your company or work or things like that, okay? So your brain develops and learns when it struggles, okay? Resist that temptation to look up answers when you're faced with a challenge, okay? You struggle through it just like, struggling through it at the gym. And you'll get so much more out of this course and also life in general when you push yourself to do the learning activity yourself rather than having someone or something like the AI do it for you, okay? I do want to talk about AI. And the truth is AI, AI is here. It's here to stay. There's no avoiding it. Like, you should learn how to use AI, okay? We don't have a class on how effectively to use AI, just like we don't have a class dedicated to learning how to search for things on Google and stuff like that. But you should learn how to use AI because it's here. Everybody is going to be using it. It's going to be part of our future. And I think that's that's the future, okay? is that companies, people, everybody, we're going to be using AI to help answer and make us more productive, okay? I don't know what the far future is going to hold, okay? But I do know, every couple months, a new version of ChatGPT is released, a new version of some model is released, and it's more capable and it's better. It's being able to do more of these complex tasks all the time, okay? At the same time, there are still limits to what AI can do, okay? And especially when you are very kind of knowledgeable on a certain subject, or if you consider yourself an expert on something, and you probe AI, all of these kind of questions, not just regurgitating information, but just can the AI think about some complex ideas? You start to see some of the limitations. And I think those limitations will continue to exist, at least in the near future. I don't know when we're going to achieve this concept of general intelligence, but that's, definitely, there's limits to what AI can do. And I don't think that's going to go away, okay? But right now, the issue that we're facing and this question of are all of our jobs going to get taken away? Okay, it's true. Right now, AI can do a whole lot of kind of base foundational stuff. Okay, it can do all of this kind of entry level job type things, and it can do that very quickly, very efficiently, and cheaply, right? Compared to hiring a real person, okay? But I don't think, I think it would be very, very unwise for any company to get rid of the junior workforce, right? People straight out of college and say oh, we don't need to hire people just graduating out of college because we could just use AI for all of these things. Because what's going to happen, in a generation, okay, they're going to have nobody with 10 years of experience who knows what they're doing, right? And all of this, all of learning, I like to picture as this pyramid, okay? You start off with a foundation in elementary school and high school, and you learn all of your arithmetic, and this is your basic stuff, right? And then as you go, you go to college, and you start to specialize in other things, right? So you take, I don't know, you have your basics math, and then you get to calculus and more complex stuff, and then here we're doing, basic machine learning stuff, right? And then at the top, you have these very complex stuff. Whatever, it's neural networks and, large learning models and all of this stuff, right? But everything kind of builds off of like previous stuff. And you've probably experienced this, right? Where you have a sequence of courses, right? Like Calc 3 builds off of Calc 2, builds off of Calc 1. And you might have been like, oh, I didn't really do that great in Calc 2. And so Calc 3 is even tougher, right? And, especially if you're like, if you were thinking, and this is a little bit of like my own story, right? Like, when, if like one class was like really hard and you didn't quite understand it, like it feels almost hopeless to keep going and do like the more and more complicated things, okay? And that's basically like a bunch of learning. And the trouble right now is that AI, it's really good at like all of this stuff here, okay? It's really good at all of this stuff. It's not so good at this stuff, okay? And so like, how do we secure a job in the future when there's all of this AI is like, we have to be able to like be good at this stuff up here, right? This is like, if you want to make sure like your job's not going to get taken over by AI, like you want to be able to like do all of this stuff up here that the AI can't do, okay? But in order for that to happen, you need to have a good foundation, right? Like if you suck at this, right? Like if you didn't get through the basic math, like maybe some of your peers, some of your friends, math wasn't their thing, okay? Well, they shouldn't go to college and study math, right? They shouldn't, they do other things, and that's totally fine, right? Like I wasn't a history person, and I'm not going to go be a history expert or something, okay? But everything's kind of building up on this, and so if this part sucks, there's no way you're going to be able to learn the complicated stuff on top. And I think this and the temptation right now, okay, and here's kind of this is the dilemma, is that this course is like right here, okay? And you're like, well, why don't you just teach us this stuff? Okay, well, I can't teach you this stuff until you have like a good understanding of this, okay? And you're gonna learn this stuff, like this stuff probably doesn't even exist yet, okay? This is stuff you're gonna like learn when you're working, okay? As you're working, like new and more complicated stuff keeps coming out, and like you're gonna learn this kind of stuff on the job while you're working and things like that, okay? But it's gonna build off of the stuff that you learn like here in your undergrad degree, right? But the problem is it's really, really tempting to use AI right now to do your homework because it's good. It's good at it, right? Like you can plug a lot of stuff in AI and you'll get a passing grade, maybe even an A on some stuff with very little effort. And so that's the tempting thing. But if you do that, you won't have this solid foundation here, all right? And then there's no hope for learning the complicated stuff. So I don't know. This is my appeal, just regarding learning in general. Is like it's true. I don't know if there's anything in this particular class that I'm going to be teaching you right now that AI can't solve on its own right now. And you might be like, well, why are we bothering learning this, right? Again, it's to kind of lay down that foundation. It's lay down that foundation so that later on, as you learn more and more complicated things, it can build off of hopefully a good and solid foundation. So I don't know. Maybe I'm preaching to the choir, but I know, like even for me, it's very tempting to just ask the AI to solve certain things for you. And I think when you have a good and solid foundation, sure, AI, you can ask AI to do that stuff, right? Like you know how to do multiplication. There's no problem with using a calculator to do multiplication, right? But if you rely too much on it, you'll lose the learning stuff. Okay. All right. So I have this other stuff about grades in life. All right. The reason why it might be so tempting to use AI is because if you believe the end goal of the course is a good grade and not learning, then of course it's going to feel like AI is the answer, right? If the goal is I just want a good grade, then yeah, using AI makes sense. Okay, but I think the goal is you're learning, and I throw this in here because this is something I struggled with personally as well. Is your grades do not define you. In high school, and I imagine all of you in high school were very good students. Okay, you all got good grades. You wouldn't be here at UCLA if that wasn't your case. And for me in high school, I built a lot of my self-worth around my grades, right? I wasn't, no surprise here, I wasn't like a star athlete or anything like that, and I wasn't like super popular. I had friends, but that wasn't like the source of my my self-value or things like that. I put a lot into like my grades and my academic achievements. And when I first went to college, I started off at Caltech, and like that was like a dream come true to go to Caltech. But it was so hard. It was so hard. I had to drop out. Okay. And during my time there, I got like my fall quarter at Caltech, I got my first C ever. And I was like, oh man. And then winter quarter, I got my first D ever. And then spring quarter, I failed like multiple classes. And, I became depressed, and I had, the problem was I had tied so much of my self-value to my grades that when I lost the grades, the ability to earn good grades, I didn't see a whole lot of value in myself, right? And it took that kind of painful experience for me to separate my identity from my grades. Anyway, I don't know where you are, and I don't know what your relationship with grades is. Okay, some of you might have a healthy relationship with grades. Some of you might be like me, or as I was, where I had this unhealthy relationship, where so much of my identity was tied to my grades. And so I just want to say, your grades do not define you. Of course, you're thinking about grad school, it's like, yeah, you want to get good grades and stuff. But again, your life is not going to be your academic achievements. Your life is not going to be your professional achievements. There's so much more to you as a human than just what you achieve in school and work and how much money you make and things like that. This sounds so cheesy, but you have the ability to love and form relationships, and there's so much more. Okay. I'd like to talk a little bit about work-life balance and stuff. Broadly speaking, there's different categories where we can put our time and energy into. And, we only have 24 hours in a day. And we can't put 100% in everything, okay? You can put energy into work, which includes school, and actual jobs and things like that. Okay, you can put time and energy into relationships, and that's going to be things with your family, friends, your romantic relationship. And then you can also put time and energy into yourself, right? Taking care of your physical health, your mental health, spiritual health, all of that. All of these things require time, and you can't just put 100% to everything. And so you have to pick and choose. You have to pick and choose what's going to be important to you. And that's, I think, where you can achieve a healthy work-life balance is by choosing what's important to you and being okay with the things that, the things that you don't put your time into, those things are naturally going to, wither away a little bit, okay? And And so what I wrote is satisfaction can be found by accepting the natural consequences of what you have chosen to deprioritize. Okay. So I wrote, work-life balance is achieved by consciously choosing what's important to you, devoting your time and energies accordingly, and in general, the more time you put in, the more you're going to get out. And then, yeah, when you can accept the natural consequences of like, I'm going to not make this a priority, this is going to go down. I think that's okay, right? And this is a silly example about like, friends and romantic partners and things like that, right? So you can imagine starting off, you're in a group of friends and you spend a lot of time together and you're close to your friends there. And then one day you get involved in a romantic relationship. And so now you're spending a lot of time with your romantic partner. Great, okay? And that aspect of your life is now flourishing because you're spending a lot of time with your romantic partner. But then the natural thing that's going to happen is you're spending less time with your original group of friends. And then the natural consequences of that is that you're not going to be as close as you used to be, right? And that might reach a point where, one day your friends go off and do something and you're not invited, or they don't expect you to come along or something. And it's not like they're being malicious and trying to get revenge on you or anything, but that's just naturally what happens when you spend less time with somebody and you spend, more time doing something else, okay? And, if you can accept that and say, hey, I'm happy with my choices. I'm happy that I've been spending a lot of time over here because this aspect of my life is flourishing. I think you can have satisfaction, right? And so as people, you get to choose what's important to you. Okay. All right. And so the same kind of thing happens with work stuff. And I put in self-care is important. Make sure you take care of yourself. Sleep is really important. That's where your body repairs itself. That's where your brain cleans up and forms memory and things like that. So make sure you take care of yourself. Okay. And when I say like, self-care is important and your physical and mental health is important, sometimes that means like not doing your homework, okay? Of course I want you to do your homework, but if there's a time where it's like, right now I need to take a day off, okay? That might mean not doing your homework. And then the natural consequence of that is if you don't finish your homework, you lose points on your homework, okay? And, there's not always a time where you can be like, hey, don't take points off of me, even though I didn't do my homework. It's like, no, you're going to lose points on your homework, but I want you to be okay with that decision and just say like, hey, I'm okay making this choice where I'm going to lose points on my homework because this other thing was more important at the time. Okay. All right. I put this thing in about fruitless entertainment. We have 24 hours in a day. We should treat each hour as precious, and there's certain activities that don't benefit us, okay? Like I'm a big fan of entertainment. I'm a big fan of doing things that you enjoy, that make you happy, because that's a big part of taking care of yourself and keeping your own kind of mental health happy, right? So spend time with friends, go on a hike, watch a TV show that you enjoy. I think those are great. But there's a certain kind of, there's apps, right, on our phone, like TikTok and YouTube Shorts and things like that, that are designed not to improve our lives and make us feel better, but they're just designed to keep us addicted and hooked. So we spend a lot of time because then they can just spam ads every now and then and generate money this way and stuff like that. And they're hijacking kind of the reward system of your brain, right? Like your brain releases little dopamine things that says like, hey, good job, you did this. And it kind of hijacks that. And so like you end up spending a ton of time and then at the end you walk away, and rather than feeling like refreshed and feeling like, oh yeah, I'm happy and life is beautiful, and I love, I love living. It's just like, oh, I feel crappy about myself, right? And if that's your relationship with certain things, like, just be mindful of that, okay? Like, don't let these things, I don't know, I feel like old man shouting at sky, but I don't know. Like, it's easy to lose time, okay? And I say this because I'm guilty of it myself, right? There's times I've just kind of like scrolled for hours, and I'm like, oh my gosh, like it's 2 a.m. now, and what happened? And now I'm gonna get like hardly any sleep, and I'm gonna feel terrible, and I don't know. Some of my best memories are from when I stayed up till 2 a.m., like hanging out with friends and like doing things I enjoyed and like having good conversation. And sure, I didn't get a good night's sleep that night, but I was happy about life, right? But sometimes now it's like I stay up until 2 a.m. doing something completely worthless, and then I wake up, the next morning I feel terrible, and it doesn't like refresh my life. So anyway, just be mindful of these things, okay? All right. So thank you for indulging me, and all right, let's get into actual lecture content here. So we'll take a look at some of the stuff from this textbook, Introduction to Statistical Learning. I also want to introduce the Tidy Models package. So when you open up your textbook, or I guess like open the PDF or whatever, it just talks about what is statistical learning, basically this concept of kind of machine learning and all of this, and talks about like what is F and all of this, and how we, all of this stuff. Okay, so the idea here is whenever we're doing machine learning, data mining, okay, we have this data, okay, and I guess this is all under the assumption that we're starting off with what we call supervised learning, is we have a bunch of variables, input variables, and then there's a response variable, and we're trying to predict the response variable, okay? So, classical examples of this are like predict how much a house is worth, okay? And so you have this input, these input variables like the square footage of the house, how many bedrooms is the house, when was the house built, and all of this kind of information about the house, where is it located, et cetera, et cetera, et cetera, okay? These count as our inputs, and then the output that we are trying to predict is how much is the house worth, okay? How much did the house sell for, right? And so the notation for how we do all of this, okay, is we have this big matrix X. X gathers all of our input variables, okay? We got n rows, p columns, okay? Each column represents an input variable, okay? We denote them as, column X1, column X2, so on and so forth, up to column XP. We have p columns. And each column is a vector of length n, okay? So because we have n observations, so column X sub j is going to be this column of, X1, X2, X3 for that particular variable. Each row represents an observation, okay? And we'll denote them as curly brace, okay? Row X1, row X2, not curly brace, I guess script writing, row X1, row X2 up to row Xn. And each row is a vector of length p because we have p columns, okay? And you have, I guess just this kind of this row vector here, right? And the entire matrix, you've got n rows, p columns. It can also be expressed as kind of just a whole bunch of these rows and something like that, right? So we have this big matrix X representing our input variables. X is going to be numeric, okay? X is going to be numeric. And you're like, well, how do we deal with categorical variables, okay? Well, we have to turn those categorical variables into numbers, right? And there's different ways to do this. We turn them to zeros and ones and things like that. And that's kind of like the magic of like large language models and neural networks and stuff like that with ChatGPT, we found a good way to turn words into numbers, okay? Because what's happening underneath the hood of these large language models is it's just multiplying a whole bunch of numbers together, okay? But we found a good way to kind of turn words into numbers and the output numbers back into words that are like things that we understand as text, okay? Meanwhile, the output variable, our column Y, this is the variable that we want to predict. This is just the column of, again, values that we want to predict. And when we talk about statistical learning, machine learning is, there's some relationship between all of those input values and that output, okay? Some relationship between Y and I wrote at least one of the X variables. And so we have some kind of function that does something with all of those input numbers, okay? And of course, some leftover error because we can't capture everything to make our prediction Y, okay? And ideally, or this error term, okay, is a random error term with a mean of 0. That, like, in the long run, the expected value of your function applied to all of your inputs will be whatever the true value of Y there is, okay? All right, and so here's just kind of a simple example here, and this is this is fictional data, but this is just to kind of say, like, all right, you have some kind of relationship between your input and the output. The input is going to be years of education. The output is income. And, how many years of education did somebody have? And we see, like, the income, there's some kind of relationship. This is fictional. It's not this clear or clean, okay? And so these are the, each red dot represents a different individual. And we're like, oh, here's an individual who had 16 and a half years of education. So, again, I don't made up data. People will say, like, oh yeah, I went to college, so that's 16 years. What is 16.2 years of education? Like, you went to college and then you took 2/3 of a summer quarter? I don't know what that is, right? But anyway, so we have these input values. We have some output values. We create a scatter plot, and then we say, all right, we want to fit some kind of line here, okay? Or in this case, we're going to say there's actually a true relationship represented by this blue line, okay? And this true relationship in blue is going to be unknown to us, but we plot, we have residuals, the difference between what we actually observed and what the true thing is. And what we're trying to do is we're trying to figure out what this true relationship is, okay? Because this is all we have, and we want to try to figure this out, right? We want to figure out the actual relationship based on the data we observed. Hopefully, we get something close to the true relationship, okay? But again, the true relationship is unknown to us, okay? So, yeah, what we're doing in machine learning, statistical learning is trying to figure out how do we figure out this true relationship, okay? And we have a bunch of different ways to kind of go for it, right? And ultimately, the main motivations for estimating this function is either prediction or inference. And I would say lately it's all about prediction, okay? But inference is trying to get meaning and insight from it, okay? In a lot of our situations, all the inputs are readily available, but the output Y isn't always that, okay? With the assumption that the error is averaged to 0, we can try to predict Y, okay, by taking kind of whatever our estimated function is. Okay, so f hat is our estimated function. And in a lot of our scenarios, we get away with treating this estimated function as a black box, okay? We don't actually care what's happening inside. We just want good predictions. That's basically like all of neural networks, okay? Neural networks are these complex, they're effectively functions. They take inputs, they do stuff with them, they produce outputs. What exactly are they doing? We don't really know, okay? We know there's like a whole bunch of multiplication. Like we can open up and list off all of the parameters in our neural network. But what does this parameter mean? What does it mean for this node to have a coefficient of 0.02? Nobody knows, okay? But you know what? We don't really care, okay? Because look at the output. The output, it's making good output, so we're happy with that, okay? But and that's kind of like if you read papers coming out of OpenAI and like all of these places working on large language models, they've given up. They've given up trying to understand what's happening, and they're just saying like, okay, what we're doing is we're tweaking around with like different inputs here, and we're seeing how it affects outputs. We're changing like reward functions and things like that, so they have like a little bit of insight, but like what exactly is happening, we don't really know, okay? And it's kind of like our understanding of the human brain as well, right? There's kind of this irony that we've come full circle. Like now we have these artificial brains, these neural networks, and we never understood the biological brain. And now we're at this point where we used to understand neural networks when they were really simple, but now they're so complex. Now it's like, okay, they've become this black box, right? And we have like some understanding of the brain. We know like there's some like chemistry going on, and this part controls like, I don't know, impulses, and this is like decision making and planning and memory and things like that. But if I open up someone's brain and we say, hey, what exactly is this neuron doing? We don't really know, okay? And we can play around with it and say like, okay, well, if I hold on to this and I put in signals like, what effect is it having a little bit? And it's kind of like that. We can start to tweak these things. But anyway, a lot of these situations, like what's exactly happening, we just treat it like a black box, and that like we don't really know what's happening inside, okay? But we just say, hey, it's making good predictions, right? Hey, this person is no longer suffering, whatever ailment they had in their brain. So success, okay? But you know what? At the end of the day, our performance, we're gonna try to separate it out. The performance is how we measure our performance by like the amount of error that we have, okay? And we say there's reducible error and irreducible error, okay? Reducible error is basically the error between our estimate of the model and the actual relationship, right? So our function is producing outputs, and how different is the actual output, our model's output from like the actual value that exists in the universe, okay? And that's the reducible error, okay? We want to try to get our model to follow kind of whatever the actual relationship in the universe is, okay? The other part is irreducible error. Irreducible error is the idea that there's going to be some kind of error that just at the end of the day cannot be captured by our model, okay? And this is going to be, this is represented by the fact that you might have two observations where all of the inputs are exactly the same, okay? But the actual value on the response is different, okay? It's like you repeat the experiment with the kind of the same conditions, right? You try to control all of your conditions as much as possible, and yet you're getting different results, okay? They might be similar, right? But you're gonna get slightly different results. And that's gonna be the irreducible error. This is kind of just the random effects that exist, the random phenomena that exists in the universe and whatnot, that, like twins, identical twins who, supposedly have like almost the same genetics, and they're raised in like the same environment and things like that, they're still going to be different. Okay, how do you explain all of that? Okay, that's the irreducible error. Okay, identical twins will be more similar on a lot of things, right? Their heights will probably be similar and things like that, but there's going to be things that are going to be still different. Okay, you have similar inputs, slightly different outputs. That's going to be your irreducible error. Okay, so this error is irreducible because no matter how well you figure out what this function f is, you're still not going to be able to get rid of this whatever error is introduced here. Okay, all right, and so the breakdown is written out this way. The difference between the actual value and whatever we're predicting. Okay, so this is our expected squared difference here. Is going to be this. The actual value is going to be f of x and this, and then the predicted is going to be f hat of x and whatever. And so this part, the difference between this and this is our reducible error, and then the variance on this, that's going to be our irreducible part. Okay. All right. As far as inference goes, okay, so the other motivation for figuring out our function f is inference. Inference is trying to like understand the relationship. And so you all took 101A, the regression course, right? That's like a requirement for this. So, and at the end of when you do linear regression, you have these coefficients, right? Beta 0, beta 1, beta 2, etc. Okay, and so beta 1 gets multiplied by input variable x1 and things like that. And you have an interpretation for that coefficient. And you say, well, if x1 goes up by 1, our prediction for y goes up by beta 1. Okay? That's the interpretability. Okay? All right? And so questions are like, what predictors are associated with the response, right? You have like this backwards and forwards variable selection, and you say, well, these are the variables that are associated with the response. What's the relationship? These are your coefficients and things like that. What's the shape that we need? And so you learn about the relationship that exists. Okay, and so linear regression is really good as far as inference goes because we can draw understanding from all of those coefficients. Okay. But as we learn a bunch of different techniques, you're going to find there are some techniques that fall better on the interpretation side, like linear regression, really good at helping us understand and interpret the results. As far as predictive power, not the best as far as predictive power, okay? And on the other end, you have things like neural networks. Predictive power, very good. Understanding what's happening, terrible, okay? All right, so how do we go about doing this? Basically, we have our training data, our inputs. So even though it looks like just an x1, this is not one number. This is a vector of input values for observation 1. And then, and this is the output of observation 1, okay, y1, right? So we have a bunch of observations, n observations. We have their input vectors x, and then the predicted value y. And we apply some kind of statistical learning method, machine learning method, or whatever to our training data to estimate this function, okay? And broadly speaking, we have parametric and non-parametric methods. As far as parametric methods go, we make an assumption about the form of the relationship, okay? So basic parametric approach is the linear model. And we say, hey, we have a linear relationship between our input variables x, okay, and our output. And basically I can just multiply each of my input variables x with some kind of coefficient, and then when I multiply them all together and add them up, we're going to get our prediction. Okay, so we take x1 multiplied by b1, x2 multiplied by b2, and so on and so forth. Let's add them all up. Okay, obviously b1 and b2 can be positive or negative and things like that. And certainly we can make more complicated things, we can say x2 is actually, x1 but squared, right? So we can, maybe one of your input variables is distance, okay? And you can do distance times some coefficient, and then you might have like your second variable is actually just your distance variable but squared, okay? And then we multiply by another coefficient, and we multiply by that, right? But at the end of the day, if you separate out your squared values and your linear values, ultimately you're just multiplying them by coefficients and adding them up, okay? So, make some assumption about the functional form, and the training the model, okay, is really just figuring out what these coefficients are, right? And that's something like linear regression. So the second part is estimating what those coefficients. We have to estimate what our beta terms are. For ordinary least squares regression, we try to minimize the sum of the squared errors, okay? You minimize your SSR, sum of squared residuals, and that's that, okay? So as far as parametric models go, parametric models, they reduce this complicated problem down to a smaller problem of just, hey, let's figure out what these coefficients are, okay? So whatever the complex, a big part is handled when you just make that initial assumption. I'm assuming there's a linear relationship, a linear form to this. And then the rest comes down to like, how do we figure out what our coefficients are? Okay, but, and so that makes it nice and simple, okay? But we run into problems if that initial assumption about, oh, we have a linear relationship, if that's wrong, then of course your model is going to be wrong, right? And so probably, I think 101A, I haven't taught 101A in a long time, but I think a lot of time is spent like checking if your assumptions are correct, right? You look at your residual plots and say like, remember, we assumed the model in the first place is linear, and was that even a safe assumption to make in the first place? So you check the residuals and you say, okay, it looks reasonable, or like, no, my residuals look terrible, and therefore probably my assumption was wrong, okay? And, you can improve things by having more and more flexible models. So you can start introducing polynomial terms, you can introduce more variables and stuff. But as you make your models more and more flexible, you have a lot more parameters that you have to estimate, right? And so now you start having to balance things out, because now you have like, this is taken into account with like the AIC and the BIC, where you get penalties for having too many parameters to estimate, or you have too many parameters and it eats up your degrees of freedom, and your adjusted R squared starts to go down and things like that, okay? And that's because all of these things can lead to what we call overfitting, where you start modeling just some random noise, okay? Random noise in your data, okay? So those are parametric models. On the other hand, we have non-parametric models. Non-parametric models don't make any kind of explicit assumptions about the functional form. And we can use these non-parametric models to fit a wide range of possible shapes for F. And when you do this, you don't have to worry, like, did I pick the wrong functional form? Because there is no functional form, right? You don't have to worry, like, oh, is it reasonable to assume it's linear? You're not making any kind of assumption like that. The trade-off with non-parametric is that usually you require a lot more data, okay? A lot more data to make any kind of accurate estimate, okay? All right, so here is an example from our textbook illustrating this. And so here, again, fictional data. We're trying to figure out the relationship between years of education and seniority. So this is kind of like, imagine some company where people are working and People make different amounts of money. Some people have been working there a long time, so they have high seniority. Some people have just started, so they have low seniority. Some people have high education, okay? Some people have less education, okay? And they make different amounts. And so perhaps the true relationship between years of education and seniority is this blue surface, okay? And we have some residuals because some of the dots are right on the surface, but some are below the surface and some are above the surface. And what that kind of represents is that you might have two people, right, with the same years of education, they've been working at the company for the same amount of time, but maybe their income level is different, okay? And there's other things that are playing into it that just aren't accounted for in our model, right? So you have two people, same amount of education, same seniority, different response variables. So you still have some residuals, okay? But anyway, this might be the true relationship, and the red dots, which are some are above and some are below the surface, are our values, okay? And what we want to do is we want to figure out, can we figure out what this surface should be, okay? And we have a few different ways we can go about it, right? We can fit a functional, this is a parametric model. This is a linear model, okay? And in this case, linear means, in 3D, a linear surface would be a plane, okay? And so here we have a relationship, years of education, there's a linear relationship, right? If you just look at along this axis, it's just a straight line, okay? Seniority, there's also just kind of a straight, flat surface, okay? And so, how well does this do in terms of fitting the original thing? It does okay, but it's not a perfect representation, right? This is the true relationship, and this is our approximation using a linear model, okay? And so some of our residuals are bigger, and that's what we have there, okay? So this only requires a couple parameters to fully specify. Really, we just need a coefficient for each of these terms, okay? But it's an inflexible model. Basically, you're limited to just fitting a flat surface, right? Whereas the real relationship should have some curvature to it, okay? And then on the other extreme end, okay, or not the extreme end, okay, here is a non-parametric model, okay? This is what we call, I guess, a thin plate spline model, all right, a spline model here. And we just said, hey, try to find a smooth, curvy surface that fits the dots as well as you can, okay? So here it's trying to find a smooth surface that fits the red dots as much as it can, and this is what it gets. And as far as like comparing the yellow surface to the blue surface, it does a pretty decent job, okay? But you get like a few weird things, right? Like there's kind of a part where it goes up, like as far as seniority goes, it goes up and then it starts to go down, okay? Where like that kind of thing doesn't exist in the actual relationship, the blue surface. So, we get a few kind of weird artifacts because it's, fitting the red dots a little bit, it's just overfitting just a little bit, okay? And if you take it to the extreme and you just say, hey, give me a surface and fit the red dots as much as possible. I want to minimize any kind of error here. And you can see there's very little residuals here. But now you get this very kind of like wobbly, bumpy surface because, it's really trying to fit the observed data as much as possible, okay? And so you have very little residuals, right? Every single red dot here is directly on the surface of this sheet, okay? But how well does this rubber sheet model the original relationship? Okay, now it's not doing as good of a job because we have overfit our data, right? So this is kind of this is the drawback of having a model that's too flexible. Okay. All right, and so in this class, we're going to be talking a lot about different trade-offs, okay? And so there's a trade-off between bias and variance. There's a trade-off between model prediction accuracy and model interpretability. There's trade-offs between everything in life, really, right? In life, you just have to say, okay, well, if I choose this, I'm going to get these advantages and these disadvantages. And if I choose this, I'm going to get a different set, right? So, what's the goal here, right? Why would we want to choose a more restrictive model instead of a very flexible one, okay? Like, why would I ever want this if I can have this, okay? All right. Well, if your goal is inference, if you want to understand how each input is affecting the output, okay, then the more restrictive models are going to be easier to interpret, okay? Yeah, question?
Is it prediction how each input predicts the output? Like inference would be you take a small sample and see how that evaluates or describes the
Yes, okay. So there's, I guess, as far as inference goes, yes, inference, we can, in kind of classical approaches, inference is like, what does a sample say about the population, okay? Here, when I'm using inference, this is kind of like understanding the relationship. We're trying to understand, based on whatever data we've observed, we're trying to make inferences about what the true relationship is in the population. So let's say we're trying to predict income based on years of education and seniority. And so the inference here is like, what is the true relationship? Based on the data I see, what is the actual, surface is that we have in the actual population, okay?
inference is in service of prediction. In order to predict, you have to do inference.
It used to be thought of that way, that if you want to make good predictions, you need to have good inference, okay? But now we can make good predictions without having good inference, okay? We can just make predictions the goal, and that's possible as well, okay? It used to be like, in order to make good predictions about income, I need to understand what is the real relationship between years of education and income. What's the real relationship between seniority and income, okay? And that could still be a valuable approach, okay? And say, all right, as years of income goes up and things like this is kind of the defined relationship that we have between the input variables and the output, okay? But now we can also just say, all right, here's a bunch of inputs. I don't really care what the actual relationship is. If I just throw the inputs into a machine and the machine multiplies a whole bunch of stuff together and it's somehow making good predictions, that's good enough for me, okay? That seems to be kind of the direction we're headed. It's not necessarily non-parametric. Like at its heart, like a complicated neural network is a parametric model because you're estimating basically all of the weights on all of the nodes on all of these things. So we have a bunch of parameters in the model. You do assume it's functional form in that you. It's like you have this layer being multiplied by this layer and this layer. So there is a functional form. It's just now we've kind of a lot of times over-specified the model in that like you might be at a point where you have like billions of parameters predicting like only like so many inputs and observations that I don't know, you can have these there's an interesting so if you run out of, in the classical approach, if you run out of degrees of freedom, like then you've overfit your model, but then you can like keep going. It used to be like you can't have more, like once you have more parameters than observations, like you run out of degrees of freedom. Okay, but now you can have like even more parameters than observations, and you've over-specified your model. And it ends up working out because now it's like you're having these different paths and stuff. So anyway, we're getting a little bit sidetracked here. But the classical approach to statistical models was we want to understand the actual relationship. And when we understand the actual relationship, we can make good predictions. Okay? And that's under the assumption that there is an actual relationship. Okay, we're assuming that there actually is some kind of surface that exists between these variables and our output. Okay, we're assuming this thing exists, and that if I just keep collecting more and more and more and more data, I'll be able to figure this surface out. Okay, that's kind of the central assumption in inference, is that it's like the population exists, there's actually a relationship there, and my limitation is that I'm not able to collect enough data. Okay, but if I'm able to collect enough data, I can figure this out. Okay. For better or worse, we're kind of, and we'll still kind of take this approach for a lot of things. I think it's still a good approach. But now we're like doing things where it's like, you know what? I don't actually care what the actual relationship is. I just want to make good predictions because that's where the money is, right? Like if I can make good predictions, I can make money. That's basically what it's come down to. We don't actually care what the understanding is, what understanding the actual relationship is. Anyway, that's what we have. Okay, so if you want to understand the underlying relationships. Okay, and that's what I kind of mean by inference here, is we're like trying to figure out like what the actual relationship is in the population based on what we're seeing in the sample here. Then restrictive models are easier to interpret and easier to explain. Okay, these more restrictive ones, they're going to be less prone to the problem of overfitting. Okay, and if you have something that's really flexible, you need lots of data to get a good fit. Okay. So, just kind of on the spectrum of things, okay? So least squares regression will be on the side of high interpretability, but less flexibility, okay? Lasso, subset, these are all kind of they play in service to least squares regression. So lasso is like an even kind of like more restricted form of least squares regression and things like that, okay? And then you have, on the other end, you have these kind of very high flexibility things, but now we don't quite understand what's happening. Neural networks, support vector machines, okay? In between, we have like trees, decision trees, okay? And then like forests, random forests, and we can make these more flexible by making them more complicated by like boosting our trees. We can make linear regression more flexible by generalizing them. We just have generalized additive models. This like fits splines and things like that. So you kind of have this, spectrum of things. For our projects, final projects, the goal is going to be predictions, all right? And so you'll probably find your best performing models to be the ones that are highly flexible, even if you can't really interpret them and things like that, okay? Most of our focus in our class is going to be supervised learning, but I do want to talk about the idea of unsupervised learning as well, okay? So supervised learning is your training data consists of both the input X and the response Y, right? And so you are able to take your inputs, make predictions, and you can compare how well your predictions match the actual outputs, okay? So that's supervised learning. You basically, it's like like how well did you learn the material, okay? You can take a practice exam, okay? And if you have the answer key, you can see how well you've learned the material, right? So if you have a practice exam and the answer key, you can say, all right, here's my practice exam. These are the answers I came up with. These are the answer keys. Oh, I got 100% on the practice exam. I've learned the material really well, right? Oh, I only got like half the answers correct. Maybe I haven't learned the material really well, right? So that's like supervised learning. You have the answers. You can see, okay, if this is how my model predicts, I can compare my model's predictions with the actual values, and we can see how well it performs, okay? Unsupervised learning, okay, is like you don't have the answers, right? So I give you a practice exam, right, and I don't give you the answers or something, okay? Now you're like, well, I think I know the answers, but until you talk to someone else, like you don't really know how well you've done, right? You don't really know how well your performance is, okay? And so with unsupervised learning, you're just kind of a lot of times looking for structure within the data. You don't have answers that you're trying to predict, and so you have like clustering methods. You're trying to group things that are similar, but clustering is tricky because, if you take any kind of group of random things and you say, like, I want you to form groups out of these things, people might cluster them differently, right? And so, clustering, dimension reductions, you don't have necessarily answers to compare against. As far as supervised learning goes, and most of our class is going to focus on this, we can further divide those into regression problems and classification problems. And this basically just boils down to what type of variable is your output, okay? So regression is where your response variable is numeric, okay? You want to do things like predict the price of a house, okay? The output is a number. This house is $500,000. This house is $1 million. This house is $220,000, okay? It's a number, right? And when it's numeric, you have a measure of how you take the difference between your prediction and the actual value. And values that are close have less error. Values that are far away have more error. So if the actual house is $500,000 and you predict $501,000, you are off by only $1,000, okay? Well, that's a good estimate, right? If the actual house was $500,000 and you predicted it's $800,000, you are off by $300,000, so your estimate is bad, right? So we can measure how far apart our things are, okay? Classification is where your response variable is categorical, okay? And here, it's either you got the classification correct or you got the classification wrong. There's not really a difference, okay? So these are things like, is the email message spam or not, okay? Or, some other kind of classification. I mean, something that, doesn't really matter. Predict the color of, I don't know, can you predict the color of a piece of candy or something, right? There's no practical application there. But, predicting color, either you predicted the color correctly, right? The color is red and you predicted red and you got it right, okay? But if you predicted green or someone else predicts blue, we can't say like the green is more wrong or the blue is more wrong, okay? They're just wrong, okay? So you don't have a measure. You can't say being off by $1,000 is less of a mistake than being off by $300,000. You either made your prediction correctly or made your prediction incorrectly as far as categorical variables go. That's kind of the broad spectrum. You do have variables that are kind of like in between, like not quite numeric, not quite categorical, like we call these ordinal variables, like ordered categorical, like clothing size, okay, small, medium, large, extra large, right? If somebody's true size is extra large, the person who predicts large is closer than the person who predicted small. And so you do have like a measure of like how right or wrong you are there. But like, what's the numeric difference and things? So, but broadly speaking, we just have numeric, where you have regression, and you have categorical, which is going to be classification. All right, so how do we measure model accuracy? I guess I talked a little bit about this already. So as far as having our models, we want to say, like, is our model performing well, right? Because if it's not, we want a better model, okay? And so for regression, we often use mean squared error, okay? And so this is going to be the difference between the actual value and our prediction, and you square them, and then you take the average, right? So mean squared error. You can take the square root of this, and that's going to be root mean squared error, RMSE. That's a common thing, but it's just basically the difference between the actual value y, our prediction y hat. We calculate the difference for every single observation we have, and we just take the average of them, okay? And so when we are working and training our model and trying to figure out, okay, what is the function, what outputs should we have, what we're trying to do is we're trying to minimize the distance between the actual value and our predicted value, right? So in linear regression, you're minimizing your sum of squared errors, which is basically this, okay? Or mean squared error. The only difference between sum of squared errors and this is the factor of 1 over n. Okay, you're just trying to minimize that. But we don't want to minimize only our the error in our training data. We really want it to generalize to unseen data. We want it to generalize to data from the real world. Okay, and so we would say that's our test data. And if you have a big set of data, you often want to split it between your training set and your test set, so you can kind of evaluate, how well it performs on unseen things. Okay. Unfortunately, there's no guarantee that the method that performs the best on the smallest mean squared error for the training data will also have the smallest MSE for the test data, right? So again, it's kind of like if somebody gives you a practice exam with answers, okay, you don't want to just like memorize the answer key. You don't want to just memorize A, B, C, D, A, B, C, D, okay? You want to actually learn the relationship between, what is the question and what's the answer. Because if you only memorize, okay, on the answer on my practice test, the answers were A, B, B, C, A, B, whatever. That's probably not going to translate over when you see an actual exam. Okay. Unless they were, very silly. But so you want to actually like learn the relationship, learn like based on the question, what's the answer, and things like that. So if you say, oh, I can get 100% on the practice because I've memorized ABC, ABC. If that's your understanding, that's not going to do well on like the real world. Okay. If you have a very flexible method, okay, its training mean squared error is going to get really small, okay? And so it'll fit the training data really well, okay? But when you do your testing on it, okay, the mean squared error for this flexible model might end up being higher than for a less flexible model, okay? So to kind of illustrate this, we'll look at like splines, and splines can generate kind of a whole bunch of range of of models and things like that, okay? Just very kind of flexible things. Or you can change the, adjust the parameters of the spline model to make them less flexible, okay? So I'm going to show you some diagrams to just kind of illustrate this concept of training mean squared error and test mean squared error and things like that, okay? And so what we're going to see is just a few examples, okay? The black line is going to represent the true relationship. Again, these are all assuming there's a true relationship between our input and our output, okay? And we are going to have 3 different models, okay? One is we can fit a straight line, okay? We can, and that's going to be orange. That's going to be the linear model. Then we'll also have a blue line, which will be a smoothing spline with a medium amount of flexibility. And then we'll have a green, which will be a smoothing spline with a high amount of flexibility, okay? And then on the right, we'll see the training mean squared error and the test mean squared error, okay? And there's also going to be kind of a flat line representing the irreducible error, okay? All right, so what is happening in this graph, okay? So the blue, the black line represents the actual relationship between x and y. There's some kind of curved relationship, okay? And then we generated random data around the actual relationship. So sometimes, and these are these circles, okay? So sometimes the random data is below the line, sometimes the random data is above the black line. And then we fit 3 models. We fit a straight line to these dots, all right? And we say, okay, if these are the dots, what's the best fitting straight line? It's this, okay? And then we also fit 2 splines. One is a medium flexibility spline, okay? Which is kind of this blue thing. And then we have a high flexibility spline, which is this green line, okay? That's super wiggly, okay? You can think of a spline. You have these different parameters on the spline, okay? And so the blue is like you have this, you're trying to fit the data, okay, with some kind of thing, and you have this big cable that, like, it's hard to make really tight turns, okay? So this is kind of like your less flexible spline, okay? And then the other is you have this, like, this thin rope that's very flexible, and you can make, like, tight little twists and turns and things like that, okay? And we said, hey, do fit the data as well as you can. Fit these dots as well as you can with the tools you have, all right? And so if you have this spline that's not super flexible, okay, you can't make these tight little twists and turns, you get this blue thing, right? And then meanwhile, you have this very flexible spline that's able to kind of adapt to the ups and downs of our observed data, okay? So this is our thing. And so this gray represents our training mean squared error, okay? So the yellow line doesn't do great, okay? Straight line, it does a poor job. It has high mean squared error, okay? The blue line does better. The mean squared error on our training set is lower. And then as far as the amount of error we measure on the green line, it does really good, okay? It's really shrunk the amount of the difference, right? As far as like this point up here, the flexible line really minimized the square difference between this dot and this, okay? And this dot and this very kind of small error. So it has very small mean squared error, okay? What we don't see is my battery's died. We don't see the test data set, okay? But the test data set, you could imagine the test data set, you could imagine being generated, okay? Again, another random set of dots that are generated around the true relationship as shown in the black line, okay? And then we say, okay, if I have random dots generated around here, okay, how well does the orange line fit? Okay, not so great. Okay, how well does the blue line fit? Okay, better. Okay, and how well does the green line fit? Okay, well, when we generate new data points, I might get like we might generate another data point like maybe down here, okay? And in this case, if there's a data point right here, or with our green line predicting up here, the amount of error is going to be quite a bit higher, okay? So because this is the true relationship, you know, you could generate a data point like right here, okay? And the green line is quite a bit far from whatever, you know, point you have there. So you can end up having higher mean squared error, okay? So if your relationship is too flexible. Yeah, question.
So for the most part, for our final project,
yeah,
we're essentially manipulating the hyperparameters of the model, changing its functional.
Yes. So yeah, for the final project, which we haven't talked about yet, if effectively is you want to make good predictions, you're going to be given some training data, okay, and then you'll have at your disposal a whole bunch of different models of which you can manipulate, yeah, the hyperparameters of your model, and do want, and effectively it comes down to like, all right, your goal is to try to get this blue line, okay, but you don't really know which line actually is like the best, right? So you're manipulating some of these things, and you only get to see the training. Okay, you don't actually know what the test thing looks like, right? So, you know, should you pick here or here or here? You only get to see the training site. And then the leaderboard will have the actual test, and it's figuring it out. And it's a difficult thing. It's a difficult thing. And yeah, there's some of you will get will get it where the test is low, and some of you will end up picking over here and get it over here, and some of you will play it cautious and get it over here and things like that. And that's what it is. Yeah, question.
Isn't it true that like a low mean squared error for the trained data doesn't translate to low mean squared error for the test?
Yeah, low mean squared error for the training data, which is this one right here, does not translate to low mean squared error for the test data.
So then, how do you like ensure that the test data has low?
Yeah, how do you ensure? That's the whole point of the class is how, so let's say you get a job in data science, okay? I imagine that's a goal for a handful of you or many of you. And what you want is you want to get the lowest mean squared error for the test data, or basically the future, the data that you haven't seen. You want a good model that's going to get this, right? But you don't have that. You don't know what's going to happen in the future. You only have like what you've observed. Okay, you only get to see this stuff down here. So how do you know? Yeah, it's tough. Okay, it's hard. And the answer is you don't, right? Like if we knew exactly the answers, like we could predict the future. Okay, but we don't. And so we have different models, and people will say, I think it should be this one, and I think it should be this one, and things like that. So my hope is in this course, I'll give you a set of tools, okay, that will help you evaluate, and that will give you clues. All right, there's going to be hints along the way. You can kind of split up your data in certain ways so you can get a sense, like, am I over here or am I over here, right? And so we have strategies, right? Basically, it's like if you get a practice exam, okay, like, I don't know, did you guys take the SAT, and like did your parents buy you like an SAT prep book or something, or maybe the AP, like you had to study for an AP exam and you got like the AP book, right? And they come with like practice exams, okay? And the way you study isn't like, I'm going to just take all of the practice exams and memorize all of these questions, right? and even you don't want to like do them all at once, right? The idea is like you learn and then you take a practice exam, and maybe it comes with like multiple practice exams so that like you can kind of check along the way, like, all right, here I've studied this much and I took the practice exam and I got this score. Later on, like, and so you kind of like intentionally hold out and not study all of the questions all at once, but like you test yourself periodically along the way. And it's kind of like these strategies that you've learned for like checking your own understanding and learning of material, like some of these things kind of translate into like, did I learn the relationship that exists? All right, am I able to make good predictions based on stuff? Okay. All right. So this is just basically all of everything I said over here. All right. And so here are some other examples. Okay. So here's like the true relationship is very close to linear. Okay. And so when we fit the linear line in yellow, okay, it does good. Okay. When we have a flexible spline, it's not all that different. Okay, from the yellow line. All right. So as far as the training error, it goes down, and then when we actually have the testing, it's something like that, right? And here you have the super flexible green line, right? It fits these dots really well, okay? And so our training error is really low. But yeah, if the true relationship is this straight line, okay, you might generate points down here. And then so, yeah, the test error is a lot higher for the super flexible model. Okay, and so these are the problems we run into. Okay, same kind of thing over here. There's the true relationship in black looks like this, and so the straight line does a terrible job. Okay, straight line does a terrible job. On the test data, it is even worse. Okay, over here the difference between the flexible blue and the medium flexible blue and the super flexible green isn't all that different. So, you get this, right? So here, on the training set, it sure goes down, and on the test set, it goes up, but only a little bit. So here, it's like it's not so terrible. Okay. But all of these things, you want to get. The hope is you get something like this, right? You don't want something overly flexible, okay? And again, if the way you're measuring, and you experience this when you took 101A, right? If the way you're measuring is only the R-squared value, okay? If your measure of success is only the R-squared value, you're going to keep every single parameter, right? And that will maximize your R-squared value, minimize your sum of squared errors, okay? But you learned like, oh, that's actually not going to be great because, and then so you have other things where you like test the significance of your coefficients and you realize, oh, these coefficients, like they're statistically not significant. So even I remove them, my R-squared value goes down, but probably that's a better reflection of reality is that I should remove these things because even if by including them, my R-squared value goes up, but not that much, okay? All right, so that's what we have. Okay, bias variance trade-off illustrates kind of this idea of this trade-off that exists, as far as our statistical learning methods, okay? And we have bias and we have variance, okay? Bias refers to the error that's introduced by modeling a real-life problem with a much simpler system, okay? So, the real-world relationships are super complicated, right? In terms of like the inputs and all of our models try to simplify it by saying like, okay, we can just collect these inputs and maybe there's 100 inputs, okay? But that's not the same thing as like the billions of different forces at play, okay? And we have, these inputs and we're trying to make our output, okay? And so bias is going to be kind of the error that's introduced there. On the other hand, variance refers to just how much your estimate for the function would change if you just had a different random training data set, right? So, you collected data, and if somebody else collected data from the same population, their values are going to be different from yours, right? And if you fit the same model, like you have this super complicated, highly flexible model, okay, your two flexible models will probably look quite a bit different from each other, okay? And so that's the variance, okay? So in general, a method that's very flexible will change quite a bit for different random sets of data, okay? So high flexible models will have high variance, right? And so we can say basically the expected test mean squared error. So the mean squared error that we can expect for any unseen test data set, okay, is going to be a combination of basically our variance plus our bias, okay, I guess technically our bias squared, plus the irreducible amount of error, okay? And mathematically it can be shown, but basically there's going to be the variance on your fitted model itself, okay, and then the bias between your fitted model and the true relationship. And so here, this is kind of an idea of the bias variance trade-off. This is the same kind of idea here. The true relationship is shown in black. I have a medium flexible model shown in light blue, highly flexible model shown in green, okay? And this is one random data set, okay? Here's another random data set, right? So the red dots are different random data sets generated. You'll see the black line stays exactly the same, right? Because I have the true relationship in black stays exactly the same. The red dots vary from just different random data sets, okay? The blue line is medium flexibility. It changes. If you pay attention if you just focus on the blue line, it just shifts around a little bit, okay? It shifts around a little bit, showing that based on the random data that was collected, there is some variance, okay? The green line changes a lot from one random data set to another, okay? High variance, okay? So based on the red dots, that green line wiggles around a lot. That's the high variance part, okay? The bias is how different is the line from the true relationship, okay? So you could imagine I repeat this like millions of times, okay? Like thousands of times. And with these green lines, they wiggle a lot. But if I did this like a million times and I took the average of all millions of those things, it will be centered probably around the true relationship of the black line, okay? But with the blue line, you can see it's consistently below the black line over here, right? Consistently, it's too low right here, okay? So there's a bias. This blue line, even if I repeat the process like with millions of data sets, and that's the statisticians or the data scientists' dreams, is have like tons and tons of data, right? But with this blue line, even if I have tons and tons of data, it is going to consistently underestimate the true relationship here, okay? And that's the bias, okay? And so what do we want, okay? Probably both of these, there's downfalls to both of those, right? There's advantages and disadvantages, okay? The advantage of the green one is in the long run, the average will get it right, okay? But right now, you don't know how good it is, okay? And it varies wildly from one random data set to another, okay? The blue one, it doesn't vary a whole lot, okay? But it is, like in the long run, it is going to consistently underestimate this part over here, okay? And so that's what this bias variance trade-off is. Okay, I've run out of time. Let's see, assessing model accuracy for classification problems. Okay, so as far as classification problems, it's similar, except you're just counting like one is the error rate, how many did you get it right versus how many did you get it wrong. And then you have similar kind of bias variance trade-offs with classification. So here's like super flexible, okay? Here with k nearest neighbors, you can have a less flexible thing, and you have similar kind of and stuff. All right, I've run out of time. I wanted to introduce tidy models. We'll get to that. We'll get to that later. Okay, all right, that's it for today. So we'll wrap things up here, and we'll see you guys, we'll see you later.